Good afternoon, everyone. Welcome to the 6th week of the live tutorial session for the point set topology course. So, today will be discuss a problem based on connectedness of a topological space. The problems are mostly towards the theoretical problem, mostly are. Some of them are might help to solve the assignment problem, but mostly are not directly related to the assignment problem. So let us start with this one, which is partly done in partly done means it is left as it is claim that this is easy. So I'll just repeat that thing. Even it is easy, that might help to get to the next second part of this problem. So problem is basically, suppose X is locally connected or even path connected, then this is satisfied if and only if every path component or component means just connected component of any open set in X is open. So if it is path connected, then every path component should be open set is open, otherwise just connected component. Okay, so the thing this path thing you can just forget, they are exactly the same proof. So X is locally connected if and by definition it is locally connected if for each point, if you consider any neighborhood around that point, there exists a neighborhood, open neighborhood inside that taken neighborhood which is connected, right? So that should imply that every component of any open set in X is open. So can someone say how to prove the forward part? Suppose X is locally connected. Okay, then you have to prove every component of any open set in X is open. Let's pick an open set. Let Q be an open set. Set in X and C be a component of it. That means connected component, right? So max component means maximal connected set, one of the maximum connected set in U. So we need to prove that this C is open. Any idea how to get this openness of C? To prove C is open, so you have to prove every point inside it is an interior point, right? That means if I take any point from C, there should exist a open neighborhood around that point which lies totally inside this C. So can you get some such neighborhood from this local connectivity of X? So let X belongs to C, enough to prove C is an interior point. Right? So now can you give me at least the open set?
Definition of local connectedness.
Which one?
Definition of local connectedness.
Yeah, local connectivity, how do you use?
We could be inside.
So your voice is not
It's a
clear
connected
somehow.
objects. But then the point X, which is contained, it's actually traveling. That's why.
Oh, okay. Uh, okay, so yes, I have to use this local connectivity of X. Sure. So the thing is here, X belongs to C and U is open. So in particular, as C is subset of U, so X is U is also a neighborhood of X. For that you use the local connectivity. Yeah, true. So as X belongs to C and C subset of U, so by local connectivity there exists some connected open neighborhood of these X that lies inside U, right? So there exists, okay, so I should also content in C is not important, but X belongs to U is important because U is an open set in X and X belongs to U, so U is a neighborhood of X. So basically I should that is use open neighborhood of X. So by local connectivity you can say that there exists an connected there exists a connected open neighborhood, let's say V. Oh, let's not take V. U and V looks almost same, so sorry. Open neighborhood, let's say A of X such that X belongs to A that totally contained in U. Okay, but if a set is connected and X is in common C and A, right? So as A and C is connected because C has I took as a component, so that is also connected as A and C both are connected and their intersection is not empty, namely X belongs to A as well as C. Intersection C non-empty, so their union is also connected. A union C is connected. Moreover, this A union C is also C contained in this and C contained in A union C, but C is the maximal maximal connected subset, one of the maximal connected subset inside U. So A intersection C cannot be bigger than that, so it has to A union C has to equal to C. But by maximality of C, this A intersection C must be equal to C, that is in particular A contained inside C, right? A union C, so A must be subset of C. So A is an open set that lies, so I took X as an arbitrary point and I show that C contained a open neighborhood around that point which lies wholly inside C. So X is an interior point. this implies X is an interior point. At siege arbitrary, so this implies siege open. So this completes the forward part. I just took any arbitrary open set and a component of that which I showed that is open, so forward part is complete. So for the converse, let's say every component of any open set in X is open, so I have to prove that is locally connected, right? Suppose component of any open set in X is open. So I have to prove X is locally connected. So again I have to pick, let's X belongs to X and U is any neighborhood. U is be any neighborhood of X in X. Okay, so I have to get one connected open neighborhood that content inside U and also X contains X, right? So any idea how to get that open set, open neighborhood, open connected neighborhood? Like U is any neighborhood of X, so I have the hypothesis for open set, so I have somehow I have to get to some open set, but as X is a neighborhood of U, so U already contains a open neighborhood inside U, right, around X. So as NPTEL of X, so there exists a open set let's say again A, open set A containing X inside U, that is this thing X belongs to A and A is contained in U, right? Now I know that now A is an open set, so by hypothesis any component of this open set A is open, right? So and that component will be connected, right, by definition. So I will consider the component which contains this point X. So that is my required open connected neighborhood around X. So consider the component C of A that contains X. Then by hypothesis or assumption, C X belongs to C. Okay, just X belongs to C, I don't need. C is an ONED, open neighborhood of X, open neighborhood, and as well as this is open neighborhood as let's it is connected, hence we have a connected, hence CJ connected open neighborhood of X such that X belongs to C and C is contained inside. So C is contained inside in this case A, because I took that to be a component of A, and A is contained inside U, so hence X belongs to C contained in U. So for any neighborhood of a arbitrary point X contains a connected open neighborhood inside that neighborhood, right? So this implies X is locally connected. Clear? So everything, if I replace just the connectivity by path connectivity, like the whole proof follows. So just you have to write, instead of connected, path connected. All the things will similarly follow. Okay, because in that case the connected, so for locally path connected, the required neighborhood here you get, that should be path connected. So again that comes from the path component of any open set, because path component is the maximal path connected subset of that set X. Okay, so whenever you have to prove the local connectivity of a space, you can prove that every component of an open set in X is open. So both the notion are both are equivalent. So from there I'm saying that, deduce that if a space is weakly locally connected at every point of a space, then it is locally connected. So suppose it is weakly locally connected. So recall the definition of weakly locally connected. So just let me recall it. Weakly locally connected. So instead of just the in the local connectivity, we need the open connected neighborhood, but in this weakly locally connected, there we don't need the openness, just connected neighborhood is enough. And as it turns out, this weakly locally connected and locally connected both are same. So in this here I am showing only weakly locally connected implies locally connected, but locally connected already will imply weakly locally connected, because if I take any neighborhood like open neighborhood, that is also any neighborhood. So that direction is trivially true. Here I am saying that the opposite is also true. Instead of taking open neighborhood, you can also take just any connected neighborhood. Weakly locally connected, so X is weakly locally connected. If for any point X, for any point X belongs to X, and a neighborhood U of X, there exists a connected neighborhood of X, say A, such that X belongs to A contained inside U. So just the instead of open neighborhood, I just replace that by any neighborhood. So the claim is weakly locally connected implies connected implies locally connected. Okay, the converse is just trivially true, so both the notion are actually same. Okay, so proof. Again, to prove the local connectedness, we will use this thing that will show every component of every open set is open. Okay. Okay, so in weakly locally connected space, component of any open set is open. Okay, so let's take an open set and its component. Let C be a component of an open set U in X. Okay, and again, to show this is C is open, I have to take a particular point, let's say pick X belongs to C, and C is already contained in U. So again the same thing, U is a neighborhood of X, then U is a basically open neighborhood, but it's fine just because in the locally, so I want to use the weakly locally connectedness, so for that U is a neighborhood, that's enough. J neighborhood of X, so by weakly locally connected, there exists again a connected neighborhood of X, there exists connected a neighborhood, let's say again B of X such that X belongs to B contained in U. Again the same argument will give you that this B should, as it is connected and X belongs to B intersection C, so again by maximality of C will give you that B is contained inside C. Okay, and as it is a neighborhood of X, so okay, just by the maximality of this thing, that will imply this one. Now as B is a neighborhood of X, so there exists a open open set that contains X inside U. Open D such that X belongs to D contained inside B, and B is contained inside C, so X belongs to D contained inside C, and that implies X is an interior point of C. Basically interior point of C. So int of C means interior point of C. So X I taken as any arbitrary point, I shown that to be an interior point. So every point is an interior point, hence C is open. So using the previous part, we claim that weakly locally connected set are locally connected. Fine. So you just have to play around the definition. Nothing much complicated is in the proof. No complication is there mostly. Fine. Everyone fine? Okay, so then let's go to the next problem. So next, suppose we are given P is a quotient map, and then if X is locally connected, then the Y is also locally connected. So basically Y is just P of X, because quotient map that is onto, so P of X is whole of Y. So if you have a quotient map, then the quotient map preserve the local connectivity, right? So here any idea how to prove this one? Again, the local connectivity, you may use the previous thing to conclude this one, if that helps. So component of any open set is open. So let's try in that way only. So let's pick any open set. So let A be any open set in Y, and C be a component of it. Okay, so I want to show that this C is open, right? For that I have to use this quotient map somehow. Okay, so to show something in here, this is open, so C is a subset, inside Y. So this C is open. If I can show that P inverse of that C is open, then we are done, because this is quotient map. I know P inverse C is open if and only if C is open, right? So if I can show, to prove C is open, will show P inverse C is open. Okay, so using or as P is a quotient map. Okay, so now can you say something about this P inverse C to show P inverse C is open? So P inverse C, can you say something to claim that this should be open? Any idea? Okay, so again this idea is almost same, like I'll show that this is union of its component and each of this component is, so basically first I should start with this A, because A is open in Y I know, so the P inverse A is open, so the component of that thing I can say only, because X is given to be locally connected. So as A is open, so P inverse A is open in X. As X is locally connected, so every component of, so every component of this P inverse A is open. Right, and this P inverse C is contained in let this P inverse C, let's say this is union of some, like any set, so I am just writing this as union of its connected component. So let's say this is union of C alpha over alpha some indexing set alpha, okay, where C alphas are components of P inverse C. Okay, so if I can show that this each C alpha is open, then I'm done. Right, so but okay, but P inverse C is already contained in P inverse A, and each C alpha is again okay, and each C alpha is a component in, okay, this, yes.
Can we write this P inverse? Can we write the, like we decompose P inverse A into its connected subclasses? No.
Nested class, but like how that helps?
Connected components.
Yeah, connected components of P inverse A, or like I don't get what are you saying?
Not sure. P is a quotient map, which means continuous and surjective. So we have used both the things.
Yeah, so yeah.
Hello.
Yeah.
Sir, X is locally connected.
Yeah.
So X is a locally connected, and C alpha is component. So C alpha is open in X.
Yeah.
And arbitrary union of.
No, like C alpha like how can I say C alpha? That's what I wanted to claim, that C alphas are open, but C alpha not component of a open set, right? I know the
Okay, sir.
P inverse A is open, so the components of P inverse A are open. So that's why I somehow want to relate this C alpha inside the component of P inverse A. But that's what I can't immediately say why this C alpha are open inside those things.
Sir, we can start from can we start from P inverse A itself?
Then
Because P inverse A is open in X and X is locally connected.
yes.
So if there is any element in P inverse A, then corresponding to that there will be a open connected component
Okay.
or set contained in the, and then if I take P of that set, if I take P both sides, then that will be a connected subset of A containing P of X.
Containing P of X. Okay, yeah, that's also maybe that way also, instead of going this way, like just directly following the definition. Okay, just let me write that phrase. Okay, let a y belongs to, let's take y from y and a neighborhood u of y in y. So there exists a neighborhood, open neighborhood, like I want to get some open neighborhood around y which contains inside u. So but as u is a neighborhood of y, there exists a open neighborhood or open set, maybe stay open, let's say A, such that y belongs to A content inside u. This implies this P inverse of A is open in X. Fine. So this I know this is open, and okay, so now let's pick an element, any element inside P inverse y maybe. Then P inverse y belongs, like, is a subset of P inverse A, so using local connectivity, okay, maybe I don't know whether this is again going in the same way. So open in X, fix X belongs to F inverse y, and X belongs to P inverse A is a open neighborhood of X. Okay. Okay, so by local connectivity, so connectivity of X implies that there exists a connected open neighborhood, let's say in this side B of X, such that X belongs to B contained inside P inverse A. So that's the local connectivity. So now my claim is that this, but the same issue is here also, right? this I know that P of B is connected, but that I don't know whether that is open. Why this P? Second thing is just the deduce locally connected, like A cross B is locally connected if and only A and B both are locally connected. But just we proved in previous class that this projection map are cosine map. So projection A cross B to A as well as B both are cosine map. So if A cross B is locally connected, then from this, as the projection map are cosine, so that will imply that A and B both are locally connected. And converse is again easy, because this, if both are locally connected, so for each point you have a connected open neighborhood around those points. So here if I consider any x comma y, so around that point you just consider the corresponding open connected neighborhood in here, right? So the connected product of open connected set is open connected here, right? So just from converse, it just easily follows from definition, and just the cosine part of this P.
Didn't get that. Could you try again?
Second part, so a projection onto pi A from A cross B to A and pi B A cross B to B are cosine map. So the topology on A cross B or product topology comes from this, so that's why they are continuous map. Okay, and A cross B is locally connected, implies AB are locally connected. Using previous part, and AB are locally connected, implies for each A belongs to A and B belongs to B with neighborhood U of A inside U of small a in A, B of B in B. There exist open connected neighborhood U prime B prime of A comma B respectively, such that A belongs to U prime contained in U, B belongs to B prime contained in B. And this implies, for if I take any, this implies for any AB belongs to A cross B and a neighborhood. So because the neighborhood will look like some neighborhood of A inside A cross some neighborhood of B inside B, and NPTEL cross B of A comma B, there exists connected open neighborhood U prime cross B prime, just obtained from this process, such that AB belongs to prime cross B prime, and that is contained in A cross B. Okay, so this implies A cross B is locally connected. Okay, just following the again just the like following the product topology definition in A cross B. Okay, so this is fine. Okay, next we have suppose an open connected subset is given, then in a locally path connected space, any open connected subset is path connected. Usually we have seen that in Euclidean space that any open connected subset is path connected, but note that the Euclidean space is already locally path connected, is also already they are locally path connected. So in this case we are generally prove that we're trying to prove that any locally path connected space, if you have open connected subset, then it will be path connected, right? So the idea is almost similar kind of idea. So you just consider the path component, and there you prove that path component is both open and closed. Usually the path components are not closed in any topological space, like in general topological space. So in this case, using the locally path connectedness, we are actually will prove that if a subset, if it is open and locally path connected, then connectedness will give you path connectedness, because we will show that is both open and closed. So in a connected subset, the only non-empty subset that can be both open and closed will be whole space. So that will give me the path component is exactly equal to the space, so hence that is path connected. So let A be an open connected subset of locally connected connected space X. Okay, and consider the path component of A. Okay, so consider C, which I'll take like path component. So I'm in particular will consider all those points which can be open connected. So it is assuming also not equal to 5 basically. Okay, so pk or fix a small a belongs to A, and consider C all the points which can be connected to A by a path. So let's say A naught. Okay, then A belongs to A such that A can be connected to A naught by a path. So this is clearly a connected set, right? Because if I can connect some A to A0 and some B to A0, then I can also connect A and B. So between any 2 points I always have a path, hence then C is path connected. Correct. Now I'll show if we can show C is open as well as close, then by connectedness of A, as already, so A0 is already belongs in this set, so that is non-empty, so the only other option is whole of A. Connectedness of A, we have C equal to A and C not equal to 5. Okay, that is the another thing, that in a connected topological space, the only non-empty set which can be both open and close is the whole set, whole space itself, right? So that's why this is C equal to A, hence H path connected. Okay, now first is, let's show C is open. C is open, so pick again a point, let's say X belongs to C, then C is a edge. Okay, what I want to, so C is already a subset of A and A is open, so by locally connectedness I know there exists a connected locally path connected, so there exists a path connected open neighborhood around X which is wholly contained in A. Okay, so A, so by locally path connectedness, there exists path connected open neighborhood, let's say D of X such that X belongs to D, that is contained inside A. Okay, so now D is path connected as well as C is also path connected, right? So and X is a common point in between them, so C union D is also path connected, right? So this implies C union D is also path connected as X belongs to C intersection D, and both of them are path connected. And now I know this D is open, and to show that this Okay, should I take C as just anything or just path component is better? Maybe path component I need instead of this C. Yeah, this will not work. I have to take C as path component. Okay. Okay. To a fixed point, that will not work because here I can't say that this D will lie inside C. That's a problem. So consider C a path component. Path component of A, okay, or non-empty. Okay, so path component, that means it will be non-empty. So okay, see the other thing you all are fine. So path component, so this is path connected. Okay, now path connected and C is contained inside C union D, again by maximality. So maximality of C will imply that C equals C union D. This implies D is contained inside C and D is open, so hence this X is an interior point. X belongs to D, contained inside C. This implies X belongs to interior of C, hence X is an interior point, hence C is open as X is any arbitrary point. Fine. So now for closedness, again let's take, so claim C is closed. So I need to show that C closure is C itself. So let's C already contained in C closure, so I have to contain, like say C closure contained in C, but let X belongs to C closure, and as by definition of C closure, this means if I pick any neighborhood around X that will intersect C, right? So take a neighborhood of X, take a neighborhood, let's say U, U of X, then U intersection C is not equal to phi. Fine, this is by closure definition. And also, as this is a neighborhood, so again by local connectivity, also by local connectivity, there exists or local, not connectivity, just path connectivity, that I also need. Local path connectivity, there exists path connected, connected again, let's again take B, path connected, path connected ONBD B such that X belongs to B lies inside U. Instead of taking U, I just have to now take the neighborhood B. Okay, so that's the thing. So this implies B intersection C is not equal to phi, as B is a neighborhood and like x like B is a neighborhood of X and X belongs to C closure, as X belongs to B, a neighborhood of X and X belongs to C closure. So instead of, I just started with any neighborhood of X, and then by local path connectivity I get a particular path connected open neighborhood, and that neighborhood again should intersect C because X belongs to C closure. So B and C both are path connected, their intersection is not equal to phi, so B union C is path connected. And once this is path connected and C is again contained in B union C, so again maximality of C will imply that B lies inside C, and already I know X belongs to B, so this implies X belongs to C. Thus C closure contained in C, this implies C is closed because C is already contained in C closure. Fine. Okay, so we just proved that C is both open and closed, so C is non-empty, hence just from this thing we get that this is any open connected subset in locally path connected space is path connected, right? So now in particular I'm saying that this openness is just needed to get this in C is open. Yes.
So capital, earlier we assumed that C was the set of all those points in A which were path connected to A naught. Then
Yes.
we assume that C is a path component of A.
Yes.
So does it still mean the same if I say
No,
C
no,
is
no, no,
the
no.
both open and
No, they are actually, the problem is that if you can prove that thing, that is fine, but there actually the problem is that I can't immediately get. So here the maximality I am using, so that subset I can't guarantee that that is maximal connected subset. So that's the problem. That's why I removed that two path components of it.
C being both open and closed, will it imply C is equal to A? No.
Yeah. Because
That's due to the fact
yeah.
that any non-empty subset which is both open and closed has to be equal to entire.
Yes, that's the connectivity. If a non-empty subset is both open and closed, then I can take like that set is just suppose C is both open and closed, then I can just take this, right, C union C complement. They are clearly disjoint, so C and C complement will give you S a person. C and C complement both are open and both are closed, but this cannot possible unless one of them is has to be empty. But C, as C is non-empty, so C is non-empty, so if it is not whole of A, then C complement will also non-empty, and that will provide a separation for the set A. But A is connected, so there does not exist any separation, so hence C has to be equal to A. Right, is it clear? So the thing that I initially started with C as just all the paths connecting a0 to this fix a0 to all points. So there the problem is to show that thing is open and closed, there will be some problem, because there I can't say anything that the union is okay, union is fine path connected, but I have to somehow show that is open. So for the taken x I have to get a open neighborhood around that. So the maximality will guarantee that C union D will lies inside C. In particular, D lies inside C. So the easily we get the neighborhood around X, which lies inside C. So the maximality is like kindly crucially used here. For that thing I can't like immediately I can't get anything. So that's why I just replace that by path component. But it's like fine, no problem in using that thing. So here I'm saying that only one path components of A is there. So if only one component is there, so like path component is there, then it has to have path connected. Then only it's possible one component is possible. Otherwise there will be at least two component. Right? Is this fine? Or still any confusion?
No, sir, it's fine.
Okay. So now in particular I'm saying a connected locally path connected space is path connected. So connected and look, so here I'm just remove the open thing, but that is fine because here I'm not working in a subset thing. So here my total space is already open. So the same thing, just instead of the open set I just took whole set as my say open set, right? So the just the same thing. So any connected locally path connected space is always path connected. Okay, so that just immediately implied. So okay, next suppose we have a topological space X, then the connectedness is same as saying that there does not exist any continuous onto map from X to a disconnected space. So that is again like very easy consequence, just to like showing the connectivity by the non-existence of any continuous onto map. In some cases if exists, so to show the non-connectedness it is sometimes useful. So as the case here I'm considering this GLNR and ON. So there I have actually such continuous onto map from the space to a disconnected space. So immediately from this thing I can say that they are not connected. So the forward part, like the both part is immediately follow just. So suppose X is connected, just will both I'll prove by like contrapositively. So suppose X is connected, then if there exists some continuous map from X to a disconnected space, if there exists some F from X to Y, so Y is disconnected, so I'm just writing that as separation of Y. So Y is disconnected. So this is a separation of that thing. So this is first of all onto and continuous. CTS continuous, okay. Then this X I can clearly write F inverse A union F inverse B, and as A intersection B is not empty, so F inverse A intersection F inverse B is also not A intersection B is empty, so F inverse A and F inverse B is also empty, and as it is onto, so that's why I can write whole this inverse as X, or so ontoness is needed to show that this F inverse A and F inverse B both are not empty, right? So here one, that F inverse A, F inverse B are non-empty as F is onto. Because of the ontoness, I only had this F inverse B and F inverse A are non-empty, and already because also A, B are non-empty, and both are non-empty. So second is they are open, because here A, B both are open as well as closed. So open or close. So as if is continuous, here the continuity is used here. So they are open, so inverse image of continuous open set under continuous map is again open or close, and this is the only thing. So non-empty, open, and X is already, so it is totally inverse of F inverse of Y has to equal to X, so that's fine. So this implies X is disconnected. Connected, which is a contradiction. So we must have the required thing. So there does not exist any continuous onto map from X to discontinuous space. Okay, so for the converse part, suppose that there does not exist any continuous map, continuous onto map from X to discontinuous space. So I want to show that this X is connected. If X is, suppose X is this AB, this is a separation. Okay, then I can define, define a map A from X, which is just AB, to, let's say, just 1 minus 1 by whole of this F of X equal to 1 if X belongs to A, and minus 1 if X belongs to B. Okay, then this is clearly onto. Clearly F is onto, and also like continuity is also there, because to check this is discrete set. So whatever topology you take, so like inverse image of phi open empty set is empty, clearly whole set is also X open. So individually if I take A inverse image of 1, then that will give me A, but as it is separation, so that is open as well as closed. So whatever one is here open or close, like it doesn't matter. So whatever you need, I have in this side. So my minus inverse image of minus 1 is again B, which is also open and close both. So whatever I need, I have. So this is clearly also continuous. Fine. So continuous onto map, which is a contradiction, because we assume that there does not exist any continuous onto map, and this 1 minus 1 is disconnected. disconnected because again you write this 1 minus 1 as a disjoint union of 1 and minus 1, so both of them are has to have like open and close, so they are disconnected. So again 1 minus 1 I'm considering with the discrete topology. Okay, so that I should mention. So discrete topology, because I could have take 1 comma just, so that thing I'm not taking. Okay, this is discrete topology. Okay, so this is disconnected, so which is again a contradiction. Hence we can't write x as this as a separation a and b, right? So and like easy consequence of this thing is GLNR and ONR are not connected. So can you produce me one continuous onto map from GLNR to some disconnected set?
Sir, determinant map.
Yeah, exactly. So determinant map, if you take the determinant map from GLNR
To R cross.
yeah, R cross, so this is just minus infinity to 0 union 0 infinity. Okay, so this is clearly a disconnection of this R cross, so this is this minus infinity 0 is open, 0 infinity is also open, so this is a disconnection of this thing. So in particular this is disconnected, and determinant map is onto because if you take any, so this map is onto, it is onto as you can take like take any as or any let's say A belongs to R cross, take, what should you take? You just take the matrix A to be just A in the first first A11 position, and remaining all are, let's say, 1, everything else is 0. Okay, the determinant of this thing is 1, determinant of this thing is A, hence and A gets mapped to there, and A is non-zero, so clearly an element of GLNR also. Okay, so A and data equal to A. Fine, so this is onto and continuous as by the definition of this determinant, it is a polynomial function in n square variable, right? So it is continuous as a polynomial function with n square variable. So I have a also R cross is disconnected, so this clearly implies that GLNR is not connected, is disconnected, so it's not connected. Similarly, the date determinant thing again will work for again ON also. So On is consists of all matrix A such that A transpose equal to identity. So if you calculate from there, the determinant will be always +1 or -1, right? Because determinant of A transpose equal to determinant A. So from here you can again take the onto map, in this case 1, -1, right? So again the same thing. So as A belongs to On implies A transpose equal to identity. Sorry, this thing is A transpose equal to identity. This implies determinant A square equal to 1, determinant A equal to +-1. So always this determinant function is first of all is well defined on this set, and for any element, so if I take 1, so you can take identity as the inverse image, and for -1 you can take just the one coordinate is -1 and other things. So exactly the same thing will work here also, because if you replace this by first coordinate by -1, then A transpose is still 1, still identity, right? So everything makes sense. So this map is again onto as well as continuous. To disconnected set, (1 - 1). So this implies On is also not connected. Okay, so this is just a consequence of that. Okay, next we like come to particular case of thing. So suppose R for the real number you consider R with cofinite topology, then R with cofinite topology is also path connected. In the usual topology, R is also already path connected, but even if you take with cofinite topology, then still R is path connected. So any idea how to proceed for this one? So for path, to show the path connected, if I like pick any arbitrary A and B from any two arbitrary real number, let's say not equal, let A B belongs to R. Okay, like usually for A equal to B, it is trivially I can take the constant path. So constant map is always continuous in this topology also, so that's not worry. So in particular you can take A not equal to B, but even that, how do you get a path, define a like path from path in between A and B? So that means you have to produce a continuous map from 0 1, so to produce a continuous A from 0 1 to R such that F0 equal to A, F1 equal to B. So can you give me one such path?
X minus A divided by B minus A. So no, X0 to A.
X0 to
X plus X A should be 0.
So you're saying just consider the linear path joining a
Sort
two.
of linear.
No, I can't hear you properly.
This is some sort of linear map, I think. But AX plus.
So x
B
plus
minus A times X plus A.
okay, a plus b minus a into x. So at x equal to 0 you get a, for x equal to 1 you get b. So why this is continuous? So if I take any let's say open set here, so that is complement of okay, complement of a finite set. So if I pull back that thing, so why that should be open here? Or in particular you can say that, so f inverse of closed set is why that is closed. So f inverse of closed set is closed. So why that is true? Let A be closed set. So a closed set inside R with cofinite topology will look like some finite set. Let's say x1, x2, xn, some. Because that's the only possible choice of closed set, because complement is open. So complement is open means that is complement of some finite set. So A has to have if A is closed, then A must be some finite set. So let this be any closed set in R with cofinite topology. And then what is F inverse A? So this, when you are defining this fx in this form, then clearly this is a like injective map, right? Because it is in moreover this is bijective onto like 0 1 onto AB if it is in the order A is less than B. If A is less than B, then it is clearly an injective map, right? Otherwise if A equal to B, then it's fine, then it is just a constant map. So in any case, so then F inverse A is at most a finite set, or so it is F inverse of x1, F inverse xn, or whole of 0 1 if A not equal to B, and 0 1 if A equal to B. So A B equal to B is not an interesting case anyway, so but still then this is the case. But this is this F inverse x1, F inverse xn, all of them are not equal if x1, x2, xn are not equal, as if A not equal to B, F is injective. Okay, so that's why you get all of this are distinct, but in any case, so this is a finite set inside your 0 1, so they are closed, right? Because we know I can take the like open set, so the complement of this thing is just will be union of open set here, right? And also F inverse x1, they are finite set, and on the 0 1 we have the induced topology from R. So induced topology from R means usual topology, right? So this is closed because the complement is the disjoint union of open set, right? So it's closed, and F inverse A is closed. Okay, so this completes that F inverse of closed set is closed, hence this is a continuous path from any A to B, so hence this is path connected. Okay, so this is easy one. So second is R with co-countable topology, that is connected but not path connected. So connectedness, can you say why it is connected? Anyone? So suppose it is not connected, so by contradiction, if this R equal to, there is some separation of R for AB both open as well as closed, in co-countable topology, then it is closed means again the A and B both are countable, right? Because open means their complement is closed, and closed set are countable set here. So then A, B both are countable. So openness I don't need, in this case I use both A, B are closed. So then A, B both are countable, but then I'm writing an uncountable set. R is uncountable as union of two countable set. Union of two countable set is always countable. This implies R equal to A union B is countable, and which is a contradiction. So hence R is connected. R is connected with co-countable topology. The second part is like bit interesting. So it is not like as the cofinite topology, it is not path connected. So what happens if there is a path between 2 points? Any guess? What kind of contradiction can you have? Okay, so again I will do it by contradiction. So let's say A, B are two distinct points. Let A, B belongs to R, two distinct points. Just a minute. Yeah, two distinct points, and there exists a continuous map. There exists continuous A from close 0 1 to R such that F0 equal to A, F1 equal to B. Now we know the continuous image. So here so once I have this A and B two distinct points, so without let's say A less than B. Okay, also okay, A less than B. Okay. Okay, so by intermediate value, so this is a continuous function from this to R. So by intermediate value theorem, that in between any this point you have also points. So also have points which include, so f of 0 1 actually so f of 0 1 will contain at least the interval AB. So A comma B, this closed thing will be contained in this set, in the whole of image, right? So in particular f of 0 1, this is uncountable. So we will contradict this fact that f of 0 1 is uncountable. Okay, so so let's consider this thing, D equal to just close 0 1 intersection Q, all the rational points. So then D is dense inside this closed 0 1. That means D closure is whole of 0 1, and this implies f of image, this thing is f of D closure. But it is easy to check that this f of D closure is actually contained inside FD whole closure, because if you take a point from D closure, so there exists a sequence that converges to that point. So once you have a sequence xn converges to x, as f is continuous, so f of xn converges to fx. So I picked x from D closure and I saw that fx is belongs to FD closure, because I already have a sequence in FD, namely fxn, that converges to fx. So fx belongs to FD closure. So it is easily followed that FD closure is contained inside FD whole closure, and FD closure is, so D is countable, so FD is also countable, right? So this is actually will be FD, as FD is countable. So image of a countable set is countable, right? So FD is countable. FD is countable, so that is closed, hence FD closure is FD. So fd is countable and f01 is uncountable, but it contains an uncountable, so this implies, so subset of a countable set is countable, so this is countable, which is a contradiction. Okay, so hence we must have this like we don't have any path in between any 2 points in R with this co-countable topology. Clear? Is this fine? Okay.
Yes.
Okay, so okay, I have one or two things there is. So interior, suppose I have a connected set, then whether the interior and closure of, okay, I should not write, this is not closure. Okay, closure is already, closure of a connected set is connected, that's fine. So interior, whether interior of that set is connected, and mainly I wanted to say this is boundary. Okay, boundary of a connected set is connected or not. So whether this is true or false, what do you think?
Interior should not be connected of a connected set.
Yeah, example. Yeah. What is an example?
Sine 1 by x.
Sine 1 by x, but that is path connected, and the boundary is again, okay, boundary is, yeah, boundary is like where you are ending in this side and that side, so okay, boundary, yeah, that okay, that's fine. So but interior is connected, right? There the boundary is not connected, because if you consider this thing, so okay, so this is bad picture, so so here the denseness is here, so this thing is getting closer to this point, let's say. So here these points are all the boundary points, and this point, so you have the boundary as this union this, so this is okay, fine, this is disconnected, but interior is the curve itself except this thing, right? Interior is the curve itself, so that is still path connected. So like you have to think of something to like union of two things where there is only one common point in between them, so that is like not an interior point in of each of them. Like there are many things, you just consider, let's say this is this thing field, and connect anything these two, this, so union, this thing totally is connected, but if you consider the interior, so these points are not there in the interior. right? Okay, maybe I have to slightly change. So basically okay, maybe just let me write the thing properly. Like this thing, the boundary are not included there. Okay, just the point is there, and these are okay. This thing, but the boundary points are not there. This thing and these boundary points are not there. Only this corner point is there, and here also the same thing. Also the same. The boundary is not there, but only this thing. So they are only connected through this point. Now the interior is not include this point, because then like any neighborhood of this thing will not be inside any of this set. But if you like, so the interior is will be disjoint union of this thing and this thing. So it is not possible, at least in one dimensional. If you have one dimensional in R, if you try to do in R, so whenever you have one point connected, the interior will be whole of this thing. But here the thing I'm doing in the subspace topology of R2. Okay, so that's why this point cannot be an interior point. So that's why it is not interior point of any of this set. But so that means the interior of this set is disjoint union of this thing and this thing, so which is clearly disconnected. So interior is not connected, and as well as boundary is also not connected. Okay, so next is again like classify some these letters up to homeomorphism, but again these things come directly from the connectivity of this thing. So M, N, Z, all of them are connected, and if they are not homeomorphic, they are homeomorphic to each other, because you can just like, for example, just M and Z. So M you can just map like this and this. Okay, so here this part, so just break the whole M into 4 parts, 1 2 3 4. So first map this part onto here, then here. So you just send the 4 separate part, 4 to 4 straight line here, and also in the Z part you just divide some. So Z also you divide into, let's say, 3 parts, and now find any bijection between these two set. Okay, so that will defines you like a homeomorphism from any of this letter. So they are all like a straight line. Okay, so you can, from there you can get a homeomorphism for that. But this is not homeomorphic to O, again due to the connectivity. So if they are homeomorphic, then if you remove one point from this thing and one point from this thing O, then they are still homeomorphic. But if you remove one point from this thing, that will be disconnected, but this is symmetric. And if you remove any point from this one, this is not disconnected, as the homeomorphism preserves the like number of connected components. So this cannot be a homeomorphism. So from there it is easily followed that these are homeomorphic, but these are not homeomorphic to O. Okay, and finally like give an example of space which is path connected but not locally path connected at any point. So again this is so whenever you have path connected, you can you know many spaces which is path connected but not locally path connected, but I'm saying that locally path connectedness you can remove from any point, so that is not locally path connected at any point. So the usual example, you know, this broom space or com space there. So for broom space, like these things, these are getting dense here, so this point is not a the space is path connected because this is union of all paths and they are all connected to a common point, so they are path connected, but not locally path connected because if you can at this point, if you take any neighborhood, that is will look like disjoint union of these things, so that is clearly not connected. You have many separation for that, but you can to remove the path connectivity, locally path connectivity at any point, you can consider, let's say this is 0 1, and you consider all the lines that connect 0 1 to all the rational points in between this thing. Let's say this is 0 1, so you consider all the lines that joins this to this, the rational points, rational coordinate cross 0, so that will never locally path connected at any of these point except 0 1. So at the 0 1 point only you have locally path connected, because here if you take whatever neighborhood you consider, that will consist of this union of these paths, so they are clearly path connected. So I have to remove the local path connectedness at this point only. So you just reflect this thing around like this line. So you do again the same thing, consider all the lines from here to here, but this point now the points is rational cross 1 at the 1 level. So join all the rational points cross 1 to this. Okay, so this is -1, this point, so 0 0, this point. So now this, if you pick any neighborhood around this point, this is still not again connected, because here together of this thing again you have this kind of also comes with this, so that will disturb the path connectivity of this thing. So this is not concretely thing, you have to check many things, but roughly this is the idea. Okay, so you have example of spaces which is path connected but not locally path connected at any of its point. Okay, so that's all I had to say. Now if any question, are there any question about which we have discussed today or anything? Yeah.
No, sir.
Okay, so then we'll stop here and again meet next week.
Thank you, sir.
Yeah. Okay.